All right, this next definition is an inflection point. So inflection point is a point in the domain of the function where on either side of that point the graph changes concavities. So it's really important, again, to emphasize that it's in the domain of the function, because you could have a graph like this where, let's say we take the graph of 1 over x. So this is the graph of 1 over x. So you can see that there's a vertical asymptote here in the middle where we divide by 0. So x equals 0 is a vertical asymptote. And you can see that on this side we have concave down, and on this side of the asymptote we have concave up. So it might be tempting to say that x equals 0 is an inflection point, but it's not. Why? Because the graph of f doesn't exist at all at x equals 0. You can't find the inflection point. So it has to be part of the domain of the function. That's really important. It's crucial here. So the function here does switch concavities, but the function's undefined where the inflection point would otherwise be. So that discredits it from being an inflection point. Okay, so to define inflection points, we essentially follow the same procedure as we do for finding critical points, except for we're going to work with the second derivative instead of the first derivative. So we'll find the second derivative, and then we'll check to see if it equals 0 or does not exist. This alone is our definition of a transition point. So if it's a transition point of f and the second derivative changes signs as we move across this location, then we sort of upgrade the classification of x equals c being a transition point to now being an inflection point. So an inflection point is a slightly stronger statement than a transition point. With that being said, let's go ahead and tackle example 2. Start with part A. We want to determine if the following functions have any inflection points. So we'll find the second derivative, first derivative, and actually let's go back a second here. Let's look at the previous page. You'll notice that these two functions that we worked with are exactly the functions over here. So we actually have all this information. Let's just copy that back over here and use what we have. So what do we know about this? Here's our sine graph for this second derivative. And then here we've got not a sine graph, but we essentially know this about u, L, and u. So focusing back here at part A, we just grabbed the information that we already found about this function from a previous example. So we can see that the concavity switches from down to up as we move across x equals 0. So because this is in the domain of the function, we already determined that, this shows that x equals 0 is an inflection point. Down here, for part B, we had this function u, L, and u, where we determined the second derivative is always positive over the domain of the function. So if it's always positive, that means it never switches to negative, which means it's never concave down. It's always concave up. So if something's always concave up, and the definition of an inflection point is that you switch concavity, that means there can't be an inflection point. So the fact that, we'll just say here, since h is concave up, let's say is always concave up, there can't be an inflection point. All right. Now g of x. So here we'll take the first derivative. which is negative 1 over x squared. Second derivative, g double prime of x, is 2 over x cubed. Now, the domain of the original function is all real numbers except 0, which can also be written in interval notation as negative infinity to 0 union 0 to infinity. This notation is a little bit more compact. This is all real numbers take away, or mod, or delete 0. So all real numbers without 0, this derivative exists. Oops. This exists on the domain of the original function. So as long as it exists on the domain of the original function, there's nothing to worry about here. So now we want to check, does g prime of x equal 0? No, it does not. Again, the only way a function equals 0 is if the numerator, the only way a fraction equals 0 is if the numerator equals 0. But 0 and 2 are not the same, so this never happens. So, in other words, this function, 1 over x, has no transition points. And since an inflection point is a transition point with the additional fact that the second derivative changes signs across that point, we know that there cannot be a point of inflection because there's no transition points. This is also the exact same example that we talked about earlier, where we have this happening. It is true that this function does switch concavities, but because the function has a vertical asymptote here, the function's undefined here. So you can't actually find the graph anywhere along this line. This gets as close as you'd like to it, but it never actually touches this vertical line, so you can't actually write down what the point is. You can't say 0, comma, whatever. It doesn't exist. So we will go ahead and say no inflection points.